So to sum up what I just said about single cycle versus multi-cycle machines, single cycle machines are basically slower. They need to be slower because, or they need to have very basic operations, and both have huge disadvantages. I mean, we're talking really basic operations now. Uh, Multi-cycle machines are better in the sense that you can divide the instructions, and your machine can be well, your slow instructions wouldn't get hurt in any way, but your fast instructions would absolutely run as fast as they can. Basically, you do not need to clog the whole system because you have a very slow instruction in your instruction set. And that basically makes you, as an architect or as a computer designer, not think about, okay, how slow is this versus, oh, I want this to work. So both single cycle and multi-cycle machines are also von Neumann architectures. You can read about the other architectures on Wikipedia or something, but they follow. I mean, this is a big thing for computer architects basically. And each instruction can be divided into 6 phases. It's basically a fetch phase where you fetch the instruction using the program counter where it points in memory, a decode phase where you try to understand what the heck does this instruction do, an evaluate address phase which basically tries to, okay, these are the operands, these are the data, the memory addresses that I should operate on. So you evaluate the address, but then you fetch, after evaluation you fetch the operands, then you execute. You basically, okay, this, I just got all the data that I needed. I execute, which is I multiply them or add them or shift them or XOR them or do something to them, and then I store the result somewhere, and that's probably in a register or in an address. There are two components to instruction processing engines. The first one is the data path, which is basically the hardware that you require to deal with data. And that would basically be the functional units that operate on the data, so fetching the data, storing the data, and so on. There is also hardware structures to it, and there is also the registers that you work with. And there's the control logic, which basically controls what the heck is the processor going to do now. What is the hardware going to do now? And where to fetch it, where, what, and these things. So, and any program's performance is basically highly dependent on both the clock cycle time, so how fast can it operate, and the average cycles per instruction. I.e., if you have a program that where you can basically have one cycle per instruction, so a single cycled processor, then CPI will be 1, and the clock cycle time will be the speed that you're going to operate with, and that speed wouldn't be like 4 gigahertz, for example, because, well, 4 gigahertz is pretty fast, and your slowest instruction will never be able to cope with it. And then the total execution time of a program would be basically the sum of all instructions for CPI multiplied by clock cycle time. So, or in other words, the average CPI. So if you have if you on average use 2 clocks per instructions per for each instruction that you run on average, and that means that basically some of them would just need 1 and some of them will need 3. So your clock, you multiply that by your clock cycle time, and then you get basically how long your program is going to run. Okay, and then, as I said, for single cycle processor microarchitecture, the CPI is 1, and for multi-cycle micro architectures, the CPI will be different for each instruction, but the average CPI should be hopefully small, so you should be working at 2-3 cycles per instruction, basically, hopefully. Okay, this is how an instruction processing looks like generically. So you have the program counter. I mean, we talked about the stages, but now we're going to cut them a bit. So you have the program counter that points to some address in the memory, fetches the program, and then the program basically is decoded. So you have an instruction decode to know what that instruction is. Then you basically fetch the memory that you need, and that memory is stored in registers. So you have the registers now, and then you can operate on things, and you store you might have the operation basically requiring more memory stuff, so you can go and fetch it more, and go in this cycle. At the end basically store whatever you need to store. So this is the data path for actually a single cycle processor. You have the PC, and the PC basically increases by 4 every time because you go, as we said, 4 is basically the size of the data that you're getting. So if you have 32-bit architecture, then 4 bytes is, you need to read 4 bytes every time because you have 1 byte per memory, and you want to read the 32 bits, right? So you need to read 4 memory words, and that basically points to the program counter to where it should go, and then that basically initiates the reading of the command to run, and then using that command you push it to the memory. You basically start reading stuff from the memory and storing it to the registers. So you have the instruction memory, read stuff, you put it to the registers, and then the registers are basically operated on by the ALU. There are some limitations with multi-cycle design, and one of them is that I'm not going to ask you what do you see with them, but let's just jump on the sweet stuff. You have very limited concurrency because now you have basically an instruction that runs for 6 cycles while it has 6 stages, right? And if you just have a multi-cycle design as is with nothing, so you run go instruction by instruction, then you are going to be basically in the first part, as we have divided the instruction into 5 or 6 parts. So if you're going to fetch, but then while decoding, the logic that you have been using for fetching is actually different from the logic that you use for decoding. That logic, the fetching logic will not be used. And then you go from decoding to loading the registers, reading the memory, for example, and then you're reading stuff. So you're using other parts of the processor while the previous 2 stages are not really used. And that basically means that you can have 4 parts of your processor idle. And this basically pushed the idea of hardware concurrency. You want more concurrency, i.e. you want higher instruction throughput. You do not want to leave your CPU unused. And that would basically mean that you might want to use these empty spaces, these empty phases in your CPU. So when an instruction is using some resources in its processing phase, you can process other instructions on the idle resources. So if right now you're doing execution and fetch is empty, then why not just start fetching? So when an instruction is being decoded, do fetching, fetch the next instruction. When an instruction is being executed, decode and fetch another instruction, and so on. And this is the whole idea of pipelining. Pipelining is a way to basically increase the concurrency of your processor by just running 5 or 6 different parts of different instructions at the same time and executing them in parallel. It's just like what happens in assembly line processing. If you have been to a factory and you're making a car, you do not basically say that, okay, I'm going to make the body now, and the people who make the engines sit idle. No, you just have people making bodies, people making engines, people making other things, and then some people assembling stuff towards the end, but then people do not block unless there is really something genuinely needed to block. So you divide the instruction processing cycle into distinct stages corresponding to the different parts of your instructions that we have mentioned. And you process different instructions at different stages. Can you think of some downsides for this? And this is what a multi-cycle for instruction look like. So if you have, suppose that you need 4 cycles per instruction: fetch, decode, execute, and write. And we have just got 2 of them. And if you do not have any parallelism, then this is the way you would do it. You just finish these 4, these 4, this 4, and this 4. While if you have parallelism, you can actually finish in half the time by just running them in that way. So while you fetch in the beginning, but while decoding the first instruction, you start fetching the second one, and then in the second time unit, while executing the first instruction, you decode the second one, and you fetch the third one, and so on. But life is not that simple, right? There are issues. I mean, first of all, you need to choose a number of stages in your pipeline. So 4, 5, 6. What is the correct number? You need to keep the pipeline correct. And that's where it gets quite interesting, because you are handling dependencies. I mean, you might be here writing, because this is the first, so you might be writing something that the next instruction will actually use. And then fetch here is meaningless, right? Because you cannot, you do not have the answer yet. So how do you fetch something when you do not have the answer yet? So you might stall on these data dependencies. But you also might have control dependencies. Suppose one of these are if statements, and you're evaluating if you basically need to jump to this instruction instead of doing this instruction. Okay? So if you fetch this one while you're not going to do it, then you're basically wasting, or not wasting resources, but not really getting the right instruction that you're going to operate with. You need to handle resource contention because, well, execution might be a bit more heavy than fetching and decoding. You might need to handle things such as long latencies in execution, for example. You need to handle exceptions and interrupts, because if you have an exception, for example, in this line, then you might want to flush everything that follows. So suppose that, for example, from an operating system's point of view, you try to fetch an instruction that is outside of your memory, of the memory that got allocated to you. And yeah, and how do you improve the whole pipeline, basically? And this is an example of a pipeline stall. You go fetch in the first T0, you start decoding here, fetching here, start using the ALU here, start decoding here, start fetching here. You need memory here, you need ALU here, but, well, you need the result from this command to actually run this. Okay? So this is what I was talking about. So now all of this has to wait. You have to stall here. So you make dependent instructions wait until its source data value is available, until the data that it needs is available, which is kind of related to the concepts that we have in multi-threading. You need to wait until the thread is actually ready. I'm sorry, I just screwed up that. Yeah. Okay. There is also the concept of branch predictions, because what you do is that, as I said, you basically you fetch the next branch prediction is basically the thing that says program counter, get me the next command. Okay? But then what might happen, as I said, is that you might have an if statement or jump statement, and you basically fetch, decode here, fetch here, do the calculations here, decode here, fetch here, and start. On this stage, you realize that, oh crap, I actually evaluated to false. And in that case, you need to do what is called a pipeline flushing. And pipeline flushing would basically mean to, remove all this work, start fetching from here. And this is an expensive process. So you want to reduce the number of times you do this. And back to the likely/unlikely cases. If you are using likely and unlikely in the if statement, then the compiler will exactly use this information to do this optimization. So if you have used likely, that I will go from this instruction likely to this instruction, then you will basically jump all of these and go there directly using the likely and unlikely directives that we talked about. If you are mistaken, then this will actually have to be flushed, and then you will need to go back to this instruction. So these are the optimizations, the kind of optimizations that we talked about in the operating systems course that actually come from the way that the architecture is. It's because of the branch predictions part. I also will talk a bit about out of order execution, which is a huge problem for threading. And that's basically that your compiler and your architecture can just go in and say, oh, you're having multiple instructions that have data dependencies. I'm just going to go grab another instruction that is independent of them and start executing it because, well, it will not result in installs in the pipeline. So I mean, if we talk about these dependencies that we had in this figure, for example, you had to wait here. So you had to block over this, and then do nothing for these. But then if you knew that there's a data dependency here, if your compiler tells you that do know that there's a data dependency here, then one possible optimization would be just to fetch this instruction instead and start running it until the output from this is ready, and then basically start fetching these ones. That basically means that the compiler and the architecture can effectively rearrange the way you wrote the program. And this is a pain in the ass when it comes to basically trying to do proper threading, because you no longer know what is going to run before what. And this can result in lots of interesting things that we're going to talk about in tomorrow's lecture. So with this, I conclude this part of the lecture. There's just a side note, something that you might want to read. It's completely unrelated, but it actually talks about somehow about the idea of changing your field. So if you're an operating systems guy, you might want to consider after a while, oh, let me just work on compilers because they are fun. Or if you're a compilers guy, you might want to consider, oh, let me just work on architecture because they are fun. And that's basically because you get fresher ideas from working in different fields. So it's not really related to the course, but it actually says that this thin, fine line that connects science is something that or computer science and engineering in general is something that is quite interesting because it gives you fresh ideas. So learning about operating systems and architecture and compilers and the way you program will make you better at whatever your end goal is. If your end goal is to be the best Java programmer in the world, you will be much better programmer if you understand how garbage collection works. And if your end goal is to be the best compilers person in the world, then you cannot be that, unfortunately, without knowing a lot of more knowledge about the architecture, and vice versa. So with this, I conclude this part of the lecture. I hope you watch it, and this is not something you're going to be examined on. So this is an extra lecture. You can view it as a tutorial or something. You might want to expand on this if you do not know this stuff. It's very cool stuff. There are lots of changing that are going on in the architecture community that you might want to check out, and that will affect you as a programmer. So thank you very much, and see you all tomorrow.